Welcome to video 4.6 in our first Principles of Astrophotography series. In this video, we discuss the physical origins of the hydrogen Balmer emission lines.
We're particularly interested in the famous hydrogen alpha line, which is present in all emission nebulae and is targeted by hydrogen alpha narrowband filters.
This video is based on section 4.6 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility.
This is a spectrum of taken for the Orion Nebula, the famous one. And a beautiful photo taken by Tran Ha, I'm not sure exactly how to pronounce his name, who gave us permission to show this image. What you're seeing here in the black curve is measured brightness as a function of wavelength. And we talked about this in the previous video, wavelengths between 400 nanometers and 700 nanometers, which is a visible range. And what you'll see in this is that for most of this whole spectrum, there's no light. But for particular wavelengths, there's a lot of light. And that's what this video, this video in particular is to focus on this hydrogen alpha, hydrogen beta, and hydrogen gamma. And in the subsequent video, we're going to focus on the oxygen 3, nitrogen 2, and sulfur 2 emission lines. But the important thing to note here is that light is emitted at particular wavelengths, not over a broad spectrum.
Principle 59, hydrogen Balmer lines. The Balmer alpha, beta, and gamma lines respectively correspond to the 3 to 2, 4 to 2, and 5 to 2 electronic transitions in the hydrogen atom.
So there are different energy levels, like we talked about in the previous video, and for the hydrogen atom, those energy levels are specified by this, it's called the principal quantum number, n. But it's just an integer. N equals 1 gives the lowest possible level, called the ground state of the hydrogen atom. And then N equals 2 gives the first excited state of the hydrogen atom, etc. There are an infinite number of transitions between all these levels because N goes all the way to infinity. In fact, one fellow that I was corresponding with said they're doing the guy who's doing radio astronomy, told me that he's looking at a state with N equals 500, which means that the electron, on average, is about a millimeter away from the proton in the hydrogen atom. So it is a huge atom. Anyway, the ones we're talking about are nowhere near that big. They're tiny, tiny, tiny atoms. And the wavelengths that produce visible emissions are these Balmer wavelengths. And all of them, you'll note, end up on level 2. So the hydrogen alpha goes from level 3 to level 2, hydrogen beta goes from 4 to 2, and hydrogen gamma goes from 5 to 2. And it's nice for hydrogen because the energy levels are actually known, and they're given by this equation. So the energy, for example, of level 2, if we put N equals 2 here, that's negative 13.6 eV. And as you'll recall in a previous video, we talked about EVs, electron volts, which is a more appropriate unit for these atomic transitions than the joule, because they're so tiny. Yeah. Divided by 2 squared, which is 4, and then you can just work out what that energy is in EV. It's awesome. And it's easy to work out what the difference in the wavelengths would be also, because for example, for the hydrogen alpha, it'll be E3 minus E2, Here we've worked out what E2 is. You work out E3 is, you plug it into that, equals h times nu, and you plug in h, and you can solve for the frequency of the photon that's emitted.
Nice.
Yeah. So these three lines are colored red for the hydrogen alpha line in the red area of the spectrum. Hydrogen beta is the turquoise, teal, whatever, cyan, blue-green. Hydrogen gamma is in the violet part of the spectrum. Yeah, just like our nice little purple. Well, it's not quite the same color as our purple principles, right? Which we call, by the way, Mercury Tracer Principle, in honor of Wren's very first car, I think, right?
Car. Bought it at auction.
Was purple. Yeah,
purple.
we called him Purple.
Yep,
I think we did.
His name was Purple.
Yeah. So this is, just know that we're honoring Wren's Mercury Tracer.
Principle 60. Standard air. Emission line wavelengths are listed for standard air of temperature 15 degrees Celsius, pressure 101.325 kilopascals, and carbon dioxide concentration of 450 parts per million.
So we talked earlier about dispersion of light, which means that the speed of light in a material such as glass or water or even air is going to be less than the speed of light through vacuum. And the differences in air between air and vacuum are big enough to be able to be measured in a lab. And so when we talk about emission line wavelengths, and we go into a lot more detail in the book about what standard air really means and how to do the calculations and everything. But if you're going to measure that wavelength, so that hydrogen alpha line, for example, comes in from the Orion Nebula, travels through deep space, which is basically a vacuum, hits our atmosphere, all of a sudden the wavelength is shorter. Mm-hmm. And so you have to take that into account if you're going to make careful measurements. And so the actual wavelengths, so as you might remember, E initial minus E final is h nu. And nu is related to the speed of light through this equation. The speed of light is the wavelength times the frequency. And so knowing the speed of light and knowing nu from this equation, you can calculate the wavelength. And that's what these wavelengths are, but corrected for standard air. And so these are the three wavelengths of the hydrogen alpha, hydrogen beta, and hydrogen gamma lines. Only one of those is typically targeted by a filter. It's the hydrogen alpha, which is generally the smart. I haven't seen an example where the gamma or the beta is stronger than the alpha, but I guess you certainly could build a filter that would capture the beta or the gamma if you wanted to.
That'd be fun.
Yeah, it'd be fun.
And these conditions are conditions that are on Earth, that exist on Earth.
Yeah.
So the 15 Celsius, the
Yes, this is pretty much, 15 Celsius is a little bit, as I remember,
cool.
We're in Fahrenheit. It's a little on the cool side, but you can also correct, once you have these wavelengths at these conditions, then...
Well, you can correct for your conditions.
If your carbon dioxide concentration isn't 450, then you can correct for that. There are equations out there.
Sure.
And we give some references to the literature to make those conversions. Thanks so much for watching.
And we'll see you next time.